Welcome to this channel. I'm Chris, and today we want to talk about set in generating systems. But before that, here's a short overview of the videos I want to take for measure theory, because the overview I uploaded was in German, so I thought I want to show you that for my English guys too. So let's get started. First, we want to talk about set and generating systems, as I said. And this video will be for sure the most technical one in the measure theory series. This is because of the axiom of choice. And yeah, so there are things we can't explain intuitively and easily because of that. But I want to try to explain as easy as possible, and hopefully you will get the essence of the statements. So let's get started. We pick a set M. So now we can start. And just for a repetition, the power set is defined as the set of all subsets of a set. So the set itself is, of course, a part of it, because trivially a set is its own subset. And what we want to do now is generalize the idea we got in the first semester in Riemann integration. So there we measured the content between the graph of a function and its coordinate system. Yeah, so the area basically. And we want to generalize that to any dimension, even infinite dimensions, but that is a video for advanced time. So let's see if I want to make a video about that. Because that leads to the so-called Bochner integral. But let's don't get into much details. We want to ask that question if we can find a function that fulfills necessary statements for our measurement. So is there a mu from the power set of Rn to 0 to infinity? Yeah, inclusive infinity, because a geometric object can, of course, have volume infinity. So first one, these are the points that the mathematicians wanted in early days. So I wrote them step by step down, because the first one, the positivity, that this function is bigger or equal 0, is already in this requirement, but let's write it down. So, and if we have an A that is congruent to B, then we want that mu of A is equal to mu of B. And what is congruent? If we have two objects, let's say two triangles, then we say that those are congruent if we can map them on each other, So by mapping, I mean really if we map them on each other, then yeah, so we can translate them into each other, yeah, by rotating and something like that. Then we want a normalization. So if we take the hyper cube of dimension n and length 1, we want that the volume of it is 1. And then we want the first strange thing called sigma additivity. But let's talk about that, and you will see that it's really necessary and useful. Yeah, if we take the union of sets AI, and it's a countable union, that's important. And then we take mu on it. It should be the same if we first map those AIs and then sum them up. And this thing for pairwise disjoint sets, that's important. Okay, what is this sigma additivity? Why do we want that? Here are two triangles, yeah, and it shouldn't be it should be the same if we first measure this triangle and this triangle, yeah, and sum them up, or if we first take both and then measure it, yeah, this should be the same, and this should be the same in an infinitesimal sense, okay? If we take really, really, really small pieces, then it should be true also. And what is the answer to this question? Is there a function like that? And the answer is no. And one might ask the question, why the hell should that not be true? And the problem is the axiom of choice. This leads to the Banach-Tarski paradox. And let's formulate it. So we take an Euclidean space E of dimension bigger or equal to 3 and take two sets of it, Mn. And of course E should have no empty interior because then this wouldn't make sense at all what we are doing here. Yeah, Banach and Tarski show that there exist partitions of M and N. Yeah, so this is a partition, so we took pieces of it and we can take those sets as the union of those pieces, yeah? And they show that those Mi and Ni are congruent to each other. What exactly are we talking about here? Take a ball in 3 dimensions, and now we destroy this ball into pieces, yeah? And they showed that we can take those pieces and glue them together to 2 balls of the same volume of the ball we had in origin. That's really not intuitive. And the proof itself is not constructive, as it uses the axiom of choice in a very essential way. So we take the group actions into account, and then we use the axiom of choice to take 1 point out of each orbit, yeah, on the sphere. This is very roughly. The proof is not that trivial. So maybe I will make a video about that at the end. Let's see. But be careful. That will be a really hard topic. This is really not trivial. Okay. So what do we do now? So the first idea is to weak the sigma additivity to additivity. This is what Felix Hausdorff did. And yeah, this is only solvable for dimensions 1 and 2. So this is not really a good solution. And what Hausdorff did here, we will call a content in near future, okay? Yeah, and what is the second idea that comes to your mind? Right, exclude those weird sets, those Banach-Tarski sets that destroy everything here. So we solve, we want a measure, better to say, restricted to a subset of the power set, yeah, and it shows a big sigma here. You will see in a few moments why. And this is really the way to solve the measurement problem. Okay, so let's talk about what very important algebraic definition. So let's take a set X and a subset big sigma of the power set. This sigma is called an algebra over X if the following holds. The empty set is in it, and if A is in it, then its complement is also in it. This is really important for the extension theorem we will look at the next video. And if we take two sets of it, the union of it should be also in it. Yeah, and we call it a sigma algebra if a countable union of those AIs is also in it. Okay. Now I wrote down some exercises. I will look at it in a video at the end of the series, so you can think of it. I wrote down some exercises which might be really interesting and important for understanding what we are doing here. So first one is prove the following. This should be and there exists no countable infinite sigma algebra on a set X. Yeah, so this should be and there. Yeah, this is surprisingly, but if you think of it a second, then you will see that it's not that surprising. Okay, and if we take this half open interval as a set, yeah, with two real numbers, then the union of a family of it then is no sigma algebra, but an algebra. And this one will be interesting for us in the next time. So this is one of the reasons why I wrote this exercise down. Okay, so now we're talking about generating systems, and if you look back to linear algebra, then you will remember generators of groups and stuff like that. So we want an analog to it for measures. in sets. Okay. So let's take an E out of the power set, where X is a set as usual. Then we call sigma of EX, which is defined by those sets whose sigma algebras with E in it are having those A in it. Yeah? So intuitively, this is the smallest sigma algebra with E in it. Yeah? This is because you have that for all sigma algebras. Okay, and we call this the sigma algebra generated by E over X. And if this sigma is the big sigma, then E is the generating system of big sigma. So now I wrote down the 3 steps to solve the measurement problem, yeah? So first we will define the terms content and measure. This is really important. And then we define continuity for it, yeah? This will be part of the next video. And also to extend continuous contents, you will see what it is in this video, on a set algebra to a measure on a sigma algebra. Yeah? And this is exactly the extension theorem of Kara-Theodori. So the first step we will look at today, and the second and third in the next video. So let M be a set algebra and X a set. We consider a map mu from M to the interval 0 to infinity. We want the following, and yeah, this should be not that new to you, because we essentially I told you that at a measurement problem, but let's write it down. Mu of the empty set is 0, and for all A, B, and M, if they are pairwise disjoint, then there holds an additivity, yeah? So this is not the sigma additivity, this is the additivity, yeah? So you can split it up into a sum. Yeah, of course you can make a sigma additivity out of it. So this, and you already know that. Okay, and if 1 and 2 are fulfilled, then we call mu content on M. And if 2 star is true, this is the sigma additivity, then mu is called a measure on M. So with that, we have the short notations of xm for measurable space, and if 2 star holds, then we have a measure space, yeah, xm mu. Okay, and this is really important for your understanding, so think about it. If we have a measure space, yeah, so mu is a measure, then mu is also a content. So speaking, every measure is also a content. Okay, that's for today. Thank you for your attention. And see you in the next video. Bye.